Hello and Happy New Year, and welcome to the January 2023 Recreational Astronomy Night Meeting, online edition of the RASC Toronto Centre. My name is Paul Markov, coming to you from Markham, Ontario. I'm always on the lookout for speakers, so if you have a presentation in mind or know of someone who could present, please get in touch with me. We have openings for the February and later meetings. Our meetings are still being held on the first Wednesday of each month. Before we start the presentations, I'd like to thank our technical team that make these presentations possible for us. And that team is made up of Andrew and Betty Reed, Ward Legros, and Emma Seabrook. We have 3 presentations for this evening as usual, and we expect to be done around 9:30 p.m. The speakers are Andy Beaton with The Sky This Month. We then have Shane Finnigan, and he'll talk to us about From Concept to First Light, my observatory build. And Debra Ceravolo will speak to us about the colors of Emission nebula. Tom Luton, our president, will close the meeting as usual with announcements. If you have questions, please enter them in the YouTube chat box, and Emma will ask the speakers the questions on your behalf. If you are attending this Toronto Centre meeting for the first time, whether you're a member or not, please let us know through chat as well. And I think we're ready to get the presentation started. Go ahead, Andy, with The Sky This Month.
Hi, my name's Andy Beaton. I'm talking from the chaos of my basement office here in downtown Toronto, and I'm here to talk about the sky this month. I'm excited to learn there are people from outside Toronto watching this over the internet, because if this was just Toronto, I'd say don't bother, it's going to be nothing but rain for the next month. But here we go. What's up? The usual list of things when I'm doing this: the big picture, key dates, the moon, planets, something in the deep sky, double star, a variable star, and whatever's coming up in the world of spaceflight. So we'll start with the big picture. This is tonight at 10 p.m. If we were to wander out and have a look at the sky after the meeting, we'd see some nice planets. We'd see all our favorite winter constellations up there: Orion and Gemini and Taurus, and all the fantastic deep sky objects that we come to expect from the winter. The moon is pretty bright, so it's not going to be an outstanding night for observing your deep sky objects, but they'll be there as soon as the moon goes away. Before the next meeting, things look very different. We're going to have the spring constellations up early in the morning, Virgo and Boötes, and even some of the summer constellations are going to start appearing. So if you're yearning for that summer Milky Way, just stay awake until 6 a.m. and it'll be showing up there for you. So the nights are not getting shorter. This is a mistake on my part. The nights are getting longer now that we're past the winter solstice. Twilight is ending at 6:19 tonight and starts again at 5:52 in the morning. So we've got a nice long night of observing. By the time we get to the end of the month, twilight will be ending probably about half hour later and starting 20 minutes earlier. So nights will be getting shorter. Still plenty of time for those long nights of collecting photons in your cameras. Important dates coming up. The new moon is on January 21st. Plan your deep sky observing around that. Oh man, I'm just typos all over the place tonight. That should be January. Uh, no, I just missed that date entirely. That should be January 7th for the apogee, where the moon is at its farthest, and perigee on the 21st. Man, I don't know what's going on here tonight. Full moon is on January 6th. Um, I don't know if there's a word for a opposite of a supermoon, a minor moon, but the moon is going to be as far away as possible when we have the full moon. It's going to be a very small full moon. Tonight is the peak of the quadrantid meteors, which is one of the better meteor showers we're going to get. And Earth is at perihelion today. That's the closest approach to the sun. So ideally, this should be the warmest day of the year if you believe in geometry. Moon events coming up. First quarter is on January 28th. Full moon on January 6th. Last quarter on the 15th, and the new moon is on the 21st. The lunar X, for those people who haven't heard of it before, is an intersection between two craters. When illuminated at just the right angle, and that's going to happen at 3 in the morning on November 1st. Oh man, I can't believe I'm getting so much stuff wrong here. Make that February 1st. Then it looks like an X shape in light against the darkness of the lunar floor. The lunar straight wall is another interesting feature. It comes from the light of the sun hitting a long rill on at a certain angle. It's much less time dependent. Anytime during the evening of January 29th, you will get to see this object illuminated in a interesting and aesthetically pleasing way. So the planets coming up. Mercury is going to be disappointing in the evening. This is probably the last night we'll see it for a while, until later in the month, then it will start showing up in the morning in the twilight. Venus is going to be our best twilight object. It's visible now, and throughout the month, it's going to be climbing higher and getting brighter. Mars is probably the most obvious planet looking overhead. It's in Taurus at sunset and will be easily visible throughout the month. It is, however, moving away from the Earth, so the longer you wait, the smaller it's going to be. I think it's just under 8 arc seconds across now, so it's getting pretty small. Jupiter is just past opposition now. Excellent target, getting smaller as it drifts away from the Earth. Right now, it's going to be setting just before midnight and setting earlier as the month progresses. It's still going to be a very good object in the western sky if you've got friends and family who are interested in looking through your telescope and wondering what the fuss is. Jupiter is probably going to be your best target. It's going to be the most spectacular of the planets. Saturn should be, but it's getting low in the west. It's going to set very early, and by the end of the month, it will be almost entirely gone. Uranus, it's just past opposition as well, so it's probably about as good as it's going to get. It'll be visible until after midnight all month long, and it's still going to be pretty much what we expect from Uranus. It'll be a small blue disk. I doubt we'll see anything like a feature with an amateur telescope, but I don't know, if you do a lot of imaging, stack up your images, you might get something. Neptune is placed even worse than Jupiter. It's closer to the horizon. It's findable, but because it's so low and so far away, you're not going to be able to see anything other than the fact that it exists. For the minor planets, Pluto's just, it's not going to happen. It's too close to the sun. Even if it weren't, it's a very difficult part of the sky to find it in, so you're going to need optimal conditions, and this isn't it. Ceres, on the other hand, is in Virgo, and if you're up in the morning, it's going to be the most interesting solar system object. It's a 7.1 magnitude, right overhead throughout the late morning, and it's going to be 0.6 arc seconds in diameter. So if you check the little chart in your observer's handbook, in theory, you should be able to get a disk with anything bigger than, say, an 8-inch telescope. In practice, let's be realistic, you probably need a bigger telescope, or you need a lot of images that you can stack up to get the noise out of there. So I always like to talk about something in the deep sky. This month I've picked the Rosette Nebula. It's a bit to the left of the constellation of Orion. It's a pretty spectacular one. Here, I'm just going to pop ahead for a second. There we go. Look at that nice red nebula with the star cluster in between. Any reasonable telescope should show it. It's a fairly bright nebula. Obviously, if you're in the city, the sky glow is going to destroy it. But anywhere in the country, you're going to should be able to see a nice donut shape. It is centered around an open cluster NGC 2244, and that's pretty bright. That's brighter than fifth magnitude. Any pair of binoculars or anything like that should see it in the city. In the country, it's going to be a naked eye object. It's interesting because that open cluster in the center is what's causing that donut shape in the nebula. The solar wind from all those bright new stars forming in the nebula are blasting a hole out in the middle. And in a few 100,000 to million years, they will disperse it entirely. I do like that nice red color. That's very good. If you're a more advanced observer interested in doing something more challenging than just finding a nebula or finding a cluster, the nebula is part of a huge molecular cloud. I've seen images that people have taken, long exposure images in hydrogen alpha. This cloud extends all through Monoceros, all through Orion, basically all through the Milky Way in that sector of the sky. It's a huge, huge blob of hydrogen gas. If you can image that, it'd be a very challenging but rewarding target. The other thing about this nebula is that the open cluster right in the middle is not the only one that's been spawned out of this this cloud of gas. There are a number of open clusters surrounding it, in and around and behind it, all part of the Colander catalog, if you want to take a look at that. Any of your usual Atlas software packages should show you a large number of open clusters around around this nebula. So we have comets and we have meteors. The quadrantids, like I was saying before, are tonight, generally running from the December 26th until January 16th. Strictly speaking, it peaked early this morning, but tonight should be a good night as well. Under a good dark sky, maybe 120 meteors an hour. The moon is going to be a problem until it gets close to setting, so I wouldn't expect a count that high, but you should get a reasonable number. Minor showers coming along the Coma Berenices running from December 5th to February 4th. Here we're looking at single-digit numbers of meteors per hour. And then we have the meteor dribbles, the ones that don't even count as a shower. We've got the alpha hydrids from December 15th to January 22nd. We have the Omicron Leonids from December 20th to January 22nd, and the Eta Corvids from January 7th to February 5th. None of these are worth going outside to look for. We're talking individual meteors per hour. However, if you are out observing and you happen to see a meteor, it might be worth tracing back to its general area of origin and see if it turns out to be one of these meteor dribbles at work. So we got comets, C2022 E3 ZTF, currently 7.4 magnitude in Corona Borealis. This is the one that all the cool kids are looking for. With any luck, and I hate to make predictions about comets because it's invariably wrong, but experts are predicting that it may reach naked eye brightness by the end of the month. So keep an eye for that. It's been a while since we've had a good naked eye comet, and I think we deserve one. We have C2017 K2 Pan-STARRS, 8.5 magnitude in Pavo. And normally I wouldn't mention this, except that I've seen that we do have observers in the southern hemisphere joining us. So you guys down there, have a look, see if you can spot this one. We've got a couple of 9.8 magnitude comets, C2022 V2 ZTF in Cepheus, C2022 A2 Pan-STARRS in Boötes, and a couple of periodic comets, 81P Wild in Libra, and 118P Schumacher-Levy in Cancer. Not particularly spectacular. They're all going to be blown out of the water by the first one, E3 ZTF, but it's always fun to find comets. Last time I did this, there were all kinds of aurora predicted for that night, and as far as I know, nothing turned up. But you never know what's going to happen. So I'm going to point out spaceweather.com as a source for up-to-date forecast maps of where we can expect to see aurora. Keep an eye on that. Just because tonight is a lousy aurora night doesn't mean that you're not going to see something good in upcoming weeks. So I like to do a multiple star just because they're interesting things to look at. And I thought, since the Orion Nebula wasn't my pick for the deep sky object, I thought I would at least go for the trapezium as the multiple star, also known as Theta 1 Orionis, and best known as the source of energy that makes the Orion Nebula glow. With a telescope, obviously you're going to see 4 super bright ones in that famous trapezium shape. There are at least 4 others visible with a moderate-sized telescope. But it gets even cooler than that. A and B stars are also eclipsing binaries. And another star has a close companion that can't be discerned from a normal human-sized telescope. So basically, we're looking at 11 stars in one obviously unstable configuration. 11 stars, there's no way it's going to stay together, so I expect in 100,000 years or so, or at most 1,000,000 years, this thing's going to scatter to the 4 corners of the nebula. I do like variable stars, as people who have heard my talks before know. Tonight's pick is BP Tauri. It's a T-tau type variable, generally going from 11.5 to 12.7 magnitude. These guys are interesting. Not only is T Taurus a star that planet orbits in Star Trek, but it's also a type of star, a very young star, which is not actually being powered by fusion yet. It's still being powered by the energy of gravitational collapse. So I'll do my usual pitch. The American Association of Variable Star Observers has been collecting data on variable stars for the past century. If you're a professional astronomer, you don't have time to look at all these things every night for years on end to gather your data. You farm it out to amateurs like us. So if you're looking for a chance to contribute to science, take your telescope out, measure the brightness of BP Tauri or any other variable star, submit it to the database, and know that you've contributed your little grain of sand to the mountain of science. So coming up for spaceflight, and for the guys running the show, this is a sign that I'm getting close to the end of my talk. JWST is still up there, still being calibrated, still new unheard discoveries coming from there, so keep an eye on that. Starship and the Super Heavy Orbital test are coming up. Once again, date to be determined. We don't know exactly when that's going to happen. There's a new launch facility on Wallops Island, Virginia, and they're going to be launching an Electron rocket as its first launch from that facility. Keep an eye on that. If you're living on the east coast of the United States, keep an eye out for a rocket being launched. If it's a nighttime launch, it should be pretty obvious. If it's a daytime launch, you'll want to be closer, but still may be visible. The Perseverance rover still driving around Mars and is now dropping canisters of soil samples for later pickup. The pickup mission hasn't been sorted out yet, but I like that we've got some future things being planned for. ISS, the International Space Station, is going to be passing in the morning until January 8th. Then it'll be out of view for us for a few days, and then from January 14th until the next meeting, it'll be passing overhead in the evening. And there's another thing, if you've got friends or family who are vaguely interested in science, but you want to show them something spectacular, show them the space station passing over. Show them the astronauts, looking down on us as they go overhead. It makes an impression on people. For times and locations, heavensabove.com is where I've been going. You can set in your own location, get your own proper times and locations for space station passes. And of course, we know it's going to be cloudy for at least part of the upcoming month, and we know it's also going to be cold, and some of us don't really want to go out in the freezing cold to do some science. Zooniverse.org is a source of citizen science projects. There are dozens of projects, many of them astronomy related, like Solar Jet Hunter, Aurora Zoo, classifying aurora as they appear and are photographed. The Super WASP Observatory measuring variable stars, you can get involved there. Planet 4 is tracking and classifying Mars weather. So if you're interested in helping out understanding the red planet, there's your chance there. And I threw this in, I just found out about it this afternoon. One more variable star happening. GK Persei, aka Nova Persei 1901, is in outburst. If you're a variable star observer, please step up and have a look at this. They're looking for a joint observing project with one of the orbiting observatories as it's gone into outburst. Everything is happening very fast here. This is a rapidly brightening star. If you get a chance tonight or the next few nights, please head out there and have a look. So thanks very much for your time, and I hope we all have clear skies.
All right, thank you very much, Andy, for a detailed The Sky This Month presentation. Let's see if we have any questions for Andy. Emma, over to you.
Yeah, we got a question coming in from Paul Markov, who wants to know, are iridium flares still happening, or are they all done?
Now, if Emma's asking me questions, I can't hear them.
Okay. Andy, can you hear me?
I can hear you.
Okay. Strangely enough, it's actually a question from myself, and I was wanting to know whether iridium flares are still happening or are they pretty much finished?
Oh, that's a good question. And I guess the honest answer to that is I don't know, but I know where I would go to find out, and that
Mm-hmm.
is heavensabove.com, where
Right.
you can enter your location and it will tell you what kind of flares you'll be expecting and where they would be.
Mm-hmm. Yeah, yeah, it just popped into my mind because nobody has mentioned them in quite some time, so I'm figuring out that they're probably done by now. They've all been deorbited and burnt up or whatever.
Yeah, that's a good question. I'll actually look that up and I'll answer it in the chat on the
Oh,
YouTube channel before the night's out.
very good, thank you. Emma, any more questions for Andy?
Nope, that's it. That's the only one.
Okay. All right, very good. Thank you, Emma, and thank you, Andy. Let's move on to our next speaker. That is Shane Finnigan. And the title of his presentation is From Concept to First Light, My Observatory Build. Go ahead, Shane.
All right. Hello, everyone. Thank you for inviting me tonight. This all started out how I posted the construction of my observatory on Facebook, and I got noticed, and that's how I got invited here. So my name's Shane Finnigan, and I live just outside of Ottawa. I'm about an hour west of Ottawa near a town called Renfrew. Lived in Ottawa all my life, but about 6 years ago, my wife and I decided to sell and move out here. Excuse me for the voice. Just recovering from some COVID here. So, anyways, we moved out here about 6 years ago, and we purchased ourselves a 150-year-old farmhouse with 7 acres of property. And through our selection of property, I tried to make sure as best as possible we could get a nice dark site so that I could eventually build myself an observatory. And when I decided to share it, I did it as a series on Facebook because I always thought it was kind of cool just to share ideas and the problems that you run into and how you solve them for yourselves. And it's like this by no means means that this is the best solution or the way to do it, but this is how I built it and it suited my purposes. And if you get anything from it, excellent. So when I announced to my friends that I was going to be building my observatory, which they all knew was just imminent as soon as we moved out here, I decided to have a little bit of tongue-in-cheek fun. So I created this Grow Your Own Observatory Seeds Pack, if it was only so easy. Um, so the site. Like I said, I have 7 acres of property. We overlook a lake. And just by serendipity or good property choice, you take your pick, the property is on a hilltop, and it actually slopes to the back of my property and to the roadway at the front of my property. So after about 2 years of living here, I had walked the property enough to figure out where I wanted to build the observatory, and it was roughly in the center of the property, which had a really good view of the south sky and fairly decent views of the east and west. Now, most of the tree line is along the perimeter, so it gave me a good opportunity to basically capture in most of the sky. And anyways, so I picked this location. And then next was the choice of what size to build. And I have to admit, I mean, it was a long process making the decisions of, finally when you're actually going to, break ground and build your observatory, do you build at 8 foot or do you say, no, I'm going to build a 10 foot because, and I'm talking diameter. So this is a round observatory. Anyways, long story short, I mean, you go through the long process, and what I came to the conclusion was 10 foot was probably the more optimal size, but given the price difference between the two, I just chose to build a 12 foot, figuring the last thing I want to do is go through the whole construction process of building an observatory only to find out that I should have built it a little bit bigger. And so I chose a 12-foot diameter. And what you see here is on the left-hand side, I staked out roughly the observatory size, and I can tell you I walked that space many, many times before we actually got to the conclusions that I just told you about. And also in the process, I was able to secure an old lamppost from a city street lighting. My brother used to work for the city, and he had recovered one from the scrap that got knocked over, and he was going to use it for a flagpole. And that was probably about 30 years ago, and he never got to it. And then when I had mentioned to him that I was building my observatory, he offered it to me. So it was like, yeah, I'll take that. So the footing on that post is 16 inches square. And excuse me for a moment. And it was probably about 35 feet long. So I actually had to cut some of it off just in order to transport it here, because otherwise I would have needed a special trailer just to do it. And living up on a property like I do, my driveway is 600 feet long, so I need a decent tractor to clear the snow in the wintertime. But it also comes in pretty handy when you have to dig holes to plant your pier. So that's what I was doing in this next picture here, was starting the dig. Now, where I'm located, like I said, I'm just outside of Ottawa, so I'm up near between Pembroke and Ottawa. The frost gets down pretty deep, so I had to dig down a little over 6 feet. And in the process, I was also thinking originally I was going to pour this gigantic slug of cement, and then I realized that I didn't need to do that. As long as I got below the frost line, I could use the weight of the soil as my stabilizer. So that's what I ended up doing. I dug down, like I said, a little over 6 feet, and inserted the post. And then, as you can see, I basically liquefied the soil as I was recompacting it and used the tractor as the compactor. Now, knowing that I was also going to be pouring a concrete slab, I was pretty confident that this was going to take care of any securing of this post and stabilizing it and making sure that I wasn't going to have any issues with it. And knock on wood, so far I haven't had any issues with it. So once I had the post inserted and the ground well compacted, then it came to trenching. So this location's about 300 feet from my house. So I actually rented a trencher just because it does a nice cleaner job than my backhoe would have. And I trenched out to the location of the observatory, but I also ended up trenching out further. So I ran water to some gardens that we have, and then out to the observatory, and out to, we also have some apple trees further out, which is off to the far right in this picture. And of course, I also ran hydro. So I ran hydro and water out to these to the location of the observatory, and buried all that in. And then came the cement. I decided on a 12-sided structure, and again, that was through some, you do the math, you figure out which is your best options, and for me, I decided that the 12-sided, I'm not sure what you would call it, a 12-sided circle, I guess. Yeah. So, anyways, I chose 12 sides, and I figured that would make the construction the easiest, as you'll see in the later steps. And then I framed this in and poured the cement. It turns out that the pad is about 8 inches thick. And again, it was a matter of making the decision of, do I pour 5 inches, or do I spend an extra $100 on cement and go with 8 inches? And as we know, I mean, at the end of the day, it's sometimes better just to do that little bit of an overbuild. And then, of course, I also have that weight sitting on top of the pier. So, and as you can see, I wrapped the pier, so it is isolated from the cement. And the other fun part was the day we decided to pour the cement. It was probably the hottest day of that summer. And we were also pouring the floor for our chicken coop. So I was using the tractor to load up the cement from the cement truck in the driveway, drive it over to one of the two locations and pour it. So it was quite the adventure, because it was just my wife and I doing this, and a little bit scary too, because you realize that once you're committed, it's there's no turning back, and if the cement starts to harden up, you're kind of in trouble. So once I had all of that done, I pre-assembled all of my wall panels. before I moved them out to actually do the assembly. So um, what I also realized was instead of trying to cut 15-degree angles, it was far easier to cut one side of the panel at 90 degrees and the other side at 30 degrees. And it actually assembles together quite nicely. And you end up with quite an easy builded construct. As you can see, it's 3 vertical studs, the 2 horizontal plates, and then it's 90 degree on one side, 30 degree on the other. So once I have the main floor in, the main floor is roughly about 6 feet once you put the floor on top of it. And then I incorporated a stairway into it. And again, that was part of the reason why I went with the 12-foot diameter was I wanted to have the stairs on the inside of the structure. And it also allowed, because of the 12-foot, just enough of space where I could put the stairs in one panel. So I can actually traverse from the ground floor up to the second floor, all within one panel, or a wall panel is what I'm trying to get at here. And then they're not quite standard stairs, but my criteria was that if my oldest daughter and my who has Down syndrome and my small dog can make it up the stairs without any issues, then I succeeded, and it turns out that they can both use the stairs no problem at all, and they're quite happy using them. So it works out quite well. So once I got the stairs in, I started putting the decking in, and as you can see, I used pressure treated for a lot of this construction, and that was just trying to foresee the possibilities of what might happen, and if any water got into the structure, I would be extra protected. And a little bit of this is always, you can plan as much as you like in your constructions, but there's always a little bit of infield figuring things out too. So in my case, it was the plate that went around the flooring had to be a little bit of ad-libbing there, but it wasn't an impossibility. It was just one of those things where you can't just nicely draw it up and predict it as much as you'd like to think you can. And then also around the doorway. So 11 panels were quite easy to build, but the door panel itself was a little bit of a custom build. So then once I had the second floor on, I put the second floor walls on. And again, you'll notice that at the doorway and beside the stairs, there was some customizing that was required there. So I had to basically build in the spot. So that's my dog there on the left-hand side, and my wife and daughter in the middle picture, so you can get a sense of how much space is actually on the first floor of the observatory. And this all went fairly well, like I said, because most of it was the pre-assembled. I pre-assembled it before I walked it out. I mean, you literally put the walls up in less than an hour and a half. So once I had the walls on and the structure around the doorway and the stairwell finished, I put the siding on, which was plywood. And again, taking into account I tried to take into account the size of materials. So, like I said, from the bottom of the top of the cement to the top of the floor was 6 feet, and then it's about another 42 inches of wall sitting on top of that. So roughly, generally speaking, you're talking about maybe 10 foot from ground to the top plate. And then once I had all the walls on, I put house wrap around that just to seal in any holes. And I had a local mill supply me with some rough cut cedar, and I used that as the siding. Now, part of the plan too was that I wanted this building to suit a farm property. So, yes, I could have used corrugated white aluminum walls, but I mean, it would have stood out like a sore thumb and really wasn't what I was looking for. I was looking for something that more suited the property, suited the environment. And I also knew that as soon as I put a building up there, my wife was going to be putting gardens around it. So it was actually part of the plan right from the very beginning, because she's a fantastic gardener, and she would just make the building look even better. So once I had that part done, then it was off to the building the roof. Now, the roof was a fun adventure in itself, because I found anyways that I kept going back and forth between many different designs. I ultimately settled for an asymmetrical roof, but not before even contacting a fiberglass company that would build radomes for radar, to see if they could build me something. And when they quoted me something around the lines of about $18,000, I realized that I'm pretty good with what I was going with. So again, I pre-built it out in my driveway. The panel in the top left is actually just plywood cut in 3 different sections, as you can see in the lower left, and then stacked to get the thickness that I wanted. So they're 5/8 plywood cut and then stacked and alternating the joints to make it even stronger. So once I had that built, and I measured across several times to make sure that I had built it round, then I started with the aperture and then built from there around. Now this I had already drawn up. I had a very good idea of what I wanted to do here, and again, the construction goes fairly quickly. So once I had the entire structure built and ready for the roofing material, it was a simple matter of picking it up with the tractor and moving it over. Now, I should say at this point, the roof only weighed about maybe 300 pounds. You could stand in underneath it and lift it up off the ground if you wanted. I mean, it wasn't easy, or I should actually, no, it was less than 300 pounds, because I could move it. But obviously, to move it up on top of the structure, you use the tools that you have available to you if it's going to make your life easier. And again, it went very easily. My son was up on the top part there, just helping guide it, and we pushed it up there with the tractor with minimal effort and no damage to anybody or anything. So this is at the stage where the roof is sitting there. Gives you an idea of overall what the structure is going to look like, and how I constructed the roof panels. So what I ended up deciding to do with is was a polycarbonate roofing material. The advantage to this was that it was extremely lightweight. It was relatively cheap, and you get the added bonus that you get some light into the building. So it actually makes it nice in there when you want to work in there. You've got good lighting, and like I said, I mean, the roof is still very, very light. I would guesstimate with the panels probably around 300, maybe a little bit more than 300 pounds. So it was easy enough. Once the roof was in place, I used the ladder to install the panels from the inside, and I had a ladder on the outside to do the perimeter, and it was quite easy to do. So the roof from base to top is about 4 feet. So once I had the panels in place, then I installed the casters. I picked up 12 of those from Princess Auto. I waited until they were on sale because I'm cheap. And each of these are rated for 300 pounds. So in theory, one caster is good enough for the entire weight of the entire roof. So I've got 11 extra just as a safety. And then to build the hatch and make it operable, what I used was it's actually a broomstick, a wooden broomstick, hardwood. And at the top there is it's a sanding pad that you can buy, metal sanding pads that have the articulations, the metal articulations, so that they bend in each different direction. So I cut that down and mounted it there so that I can use the broomstick to screw it in place and then lift it up, open my hatch, and it also secures the hatch at the same time. And then when I'm finished, basically I unhook it, lower it down, and I can secure my aperture for when it's not in use. So this was pretty much probably August timeframe, August, yeah, around there. and I had mostly finished the construction of the building. I did run into a number of issues with getting the roof to rotate properly, and it was mostly because of how I was using, trying to guide the roof. So that was a bit of a learning curve. But I was at least able to say that I have an observatory now, so I christened it, and seeing that I'm located close to the Madawaska River, I decided I'd call it the Madawaska Optical Observatory, or MOO for short. I figure you always have to be able to laugh at yourself, so I go visit MOO regularly. And then these are some close-up shots. You can see in the top left the latch, what I use to hold the aperture down when it's not in use. I have a wide shot there with some rope lighting that I haven't yet mounted, and then you can also see the casters at the interface between the roof and the walls. And at that point, I also have the aluminum flashing. So I have aluminum flashing in an L shape there, and then on the outside, the roof also mimics a reverse L. So for anything to come in, it literally has to do two 90-degree turns. The top plate, I had a good friend of mine who's also a gunsmith, and he has his own machine shop create this for me. So I just drew it up for him, told him what I wanted, and then he cut it for me and built it. And then the top of the pier, I calculated out where I wanted my my mount to sit relative to the floor. So if I was looking at the zenith with my telescope, where exactly would I would be situated. And then I cut the pier off at that space, sanded it to about as flat as I could, basically using a large board with sanding paper stapled to it, and just keep working it with the sandpaper and the level until I got it to what I was happy with. Then I mounted the top plate. So that was the end of the first year construction. It was more or less done at that point, but there was still many steps that I wanted to do. And as you can see, I have the telescope mounted there, and that was 2020. So I was actually looking at Mars for that. I actually had my observatory built, so I was able to observe Mars at its closest. So the next year, I continued with my construction. One of the very first things I did was I decided that I didn't want to be walking through mud to get into my observatory, so I poured myself a cement pad. And then on the inside, I did a few final finishing touches, but one of the things that I always wanted to do is I never wanted to leave it as the open structure stud walls. So again, I went to my local mill and I got some basically rough cut cedar that he had kicking around that had already turned gray a little bit, and he didn't really have a use for it, and picked that up, and I sided my walls with that. And then I also found a crate that had made in Canada on one of the planks, so I used that within the construction so that you could be reminded where you are in case you forgot. So again, here's another wide shot with the walls completed. You'll notice that above the doorway, I've enclosed that in so I have a little bit of a desktop surface. And I also put in basically just a Craftsman tool case where I keep my eyepieces and various accessories that I use quite often. And you can also notice that I have along the roof on right where just above the casters, you'll notice that that's where the post is that I use to lift the aperture. And you'll also notice that there's some bungees on there. And I learned that it's always good to bungee the that post securely, because I have had on one occasion that scared me a little bit was I caught just enough of a breeze that it lifted the door and the post out of its hook, and it was just floating there. So not that if it came crashing down, it wouldn't have hit anything, but I just didn't want to take the risk of anything getting damaged. So since then, I use these bungees, and it works really, really well. It's never moved since, and I'm quite happy with it. Again, like I said, I mean, the solutions work for me. So you know, I take that for whatever it's worth. I realize that some people are going to look at this and go, I wouldn't do it this way. And it's like, I totally appreciate that. It's one of these projects where you're building it for yourself. So you have to, you know, take that into consideration when you're looking at other people's builds. I also have, you'll notice roughly in the middle on the back wall and off to the left, a chain there. And those are chains that I use. There's a better picture of it here, that I use to secure the roof down. So I just use a cabiner on one end, and it's bolted to the structure on the other end. The lighting, I have a white light, rope light, and I also have a green dimmable LED rope light. So when I'm observing, I can use the green light at its lowest setting, and it's very good for the eyes. It's nice to work with. And then if I'm just in there doing something and I need a work light, I use the white light. So in the summertime, I have a block of wood that I use to just vent the roof. I'm up there working. And as you can see on the right-hand side, I've got a power bar there. I also have another power bar right on the post. And so I've got no shortage of power where I need it. And what was I going to say here? Oh yeah, on the top pictures here, I have what I used was the floor mats that you get for you know, kids' playrooms or your gym or whatever, and I used that and I stacked them together and I made that for my eyepieces. And it's quite an easy process actually. What I did was I used a tin can and the type of opener that takes the rim right off the edge, so you've got that very sharp edge. And I've got a tin can right here just to show you. But essentially, it just cuts the edge right off of it. And then what I did was I straightened that out with a screwdriver. And then you literally take that and push it right through those foam blocks. And it cuts really nicely. And I was able to cut all of those holes for my eyepieces with minimal effort. Nice, clean, round holes. And it cost me a can of soup, which I got to eat too. So on the far left-hand side, you can see a picture that was taken earlier this summer with the gardens in full bloom around the observatory and my beehive just off to the in the distance on the left-hand side. So with regards to the roof, in our area, we have experienced some pretty severe storms like most people. We've had some high winds where I've had trees come down. You name it. I've had some pretty nasty weather and the roof has not budged. So those three chains on there there's just enough slack to be able to unhook the cabiner. But other than that, there is no slack. And I haven't had any issues. Again, no water coming in, no snow coming in, and the roof remained in place during some pretty severe storms. So also what I discovered too was Shane's incredibly lazy, and that is for the first year I only had the my 150 Esprit mounted, and I found that whenever I wanted to do solar observing, I had to take that scope off and put my 150 hydrogen alpha Lund on there. And what I found was a lot of times I didn't want to. And it was not that it was physically difficult, it was just then you have to rebalance it and you have to repoint and do all of the other fun stuff when you change your scope. So I realized that it was just far easier just to dual saddle mount it. And it just made it that much easier. I mean, that's the whole point of an observatory in the first place, is you're trying to make your setup times and your pack down easier. And yeah, the point of it is when it's easy to use, you're going to use it more often. And I can tell you, right, I use this a lot of times now. I can get more observing done in probably just a few days than what I used to do in a year and a half, just because when we lived in the city, I had to travel out to a darker location, do the setup, and then do the pack down and get it all back home. And then of course you have to lay out all your equipment afterwards to get rid of dew and what have you. So again, just some general shots. Through the wintertime, I clear a path so that I still use it in the wintertime. I do solar observing. So you'll notice that I have a shield for my laptop that I built, just to help allow myself to see the screen better. And then just some general shots of the overall area. I mean, I think it's not nice to the environment. It's pleasing on a farm property, and it didn't cost much to build. Honestly, I was actually surprised at how little it cost to put it in. I mean, obviously a lot of sweat equity, but it's very much worthwhile. What I've learned about observatories is I would highly recommend anybody that has the space and time to build one to do it, whether you're in the city or not, because even if you're in the city, there's the planets, there's the moon, there's the sun, and having your equipment readily accessible to use means that you will use it far more often. And that's the whole point of it. So on the right hand side here is just a picture of the Milky Way from my property that I took there earlier this summer, just to give you an idea of what kind of sky I have. So reasonably dark considering where I am, and I'm quite happy with it. I also failed to mention that on my pier, before I put the cap on for the mount, I did fill the post with sand to help dampen some of the vibrations, because obviously it was quite a long post. And I can honestly say that I'm very happy with it. I don't have any movement. I've been able to do some imaging that I'm quite pleased with. And as I said, I've used my observatory so much now that I can't say enough nice things about having an observatory available. So if you ever have the chance, I would highly recommend you build one. And I just wanted to show you one last thing, and then I'll wrap it up here. But just because this is the type of person that I am, I built this when I was conceptualizing the building, just so that I had a good idea of what I was getting myself into and how it would look on the property. So basically, I just built a scale model out of cedar, and it just helped me, like I said, work through some of the problems on the construction. Just you want to try to save yourself the problems of running into something in the field once you're actually building it. So this helped me do some of that. Now the roof wasn't asymmetrical, but that was also part of a previous design that I ended up abandoning. So, and that's about it. I mean, like I said, I just wanted to share it so that everybody had the opportunity to, if you get any good ideas out of it, I mean, take them and run. I mean, that's the whole point of sharing it. And that's about it. So thank you very much.
Thank you, Shane. That's a fabulous observatory that you've built, and great carpentry skills to pull it off.
Oh, thank you.
And thank you so much for sharing it with us. I'm glad I found you on the internet to show us this. Do we have any questions for Shane?
Yes, we do. Shane, can you hear me?
Yes, I can.
Great. The first question comes in from Guy. How does a polycarbonate roof handle heat inside the observatory?
On the really hot sunny days, it can get a bit toasty in there. And what I've discovered is just using a fan, and I have some venting that I've since installed. I don't have any problems. I mean, we're also blessed with living in an area of the world where, it's not going to get. We're not Arizona hot, is what I'm trying to say. So, if I was in Arizona, I probably wouldn't recommend it. But if I was in a more temperate zone like where I am at, it's a workable design.
Great, thank you. Next question comes in from Andy Beaton. Are there problems with the wind when the lid's open?
Surprisingly, no. What I discovered was when I do lift my aperture and have it in place, if it's really windy, it ends up acting like a sail or basically like a weather vane. So it will move my roof for me. But I haven't had any observing issues. I haven't had any issues where the wind lifted it off. And I mean, I could automate my observatory if I really wanted to, but what I've discovered was I'm one of those weird few that just like to be out in the observatory and enjoying the environment at the time. Get to listen to the coyotes and the owls and observe. So, but yeah, I haven't had any problems with the wind.
That's great. The next question comes in from Stephen Douglas. Was a building permit required? If so, how did that go?
Well, I was fortunate enough that I'm built just underneath the size that I need, and being a round building, it gets you to play around a little bit. So I was able to not have a building permit or not require a building permit. So
that's great. Next up, did you consider a roll-off, and what made you decide on your design?
I did. I looked at so many different designs. It's crazy, and it's when you finally have the property and the desire to build something, and then you start thinking of every possible thing. And ultimately what it came down to is I'm not really a fan of roll-offs, and it's like, no offense to anybody that has them. They do a great job. It was just for my purposes, I was trying to avoid having that additional structure from the building. And I also knew that I wanted to build a 2-story building. So building it with a roll-off would have been a little bit more challenging. So I did look at building a roll-off, but I quickly abandoned it for the reasons that I mentioned. And I should mention the reason why I had wanted to build a 2-story was I had read long ago, and whether it's true or not, I don't know, but we can debate this later, that there was a considerable amount of ground effect within, the first 6 feet or 7 feet of closest to the ground, where you get a lot of turbulence, you get a lot of moisture. So my theory was that if I could raise myself up even just a little bit, one, I benefit with the horizons, but I also benefit with getting myself out of at least, that the thickest layer of muck that, I realize we're only talking 6-7 feet, so it's not anything crazy, and I do find that I think I can say that there is a difference. But what I have noticed was with the observatory is I've never had to use my dew heaters since I've built the observatory, not once. And I've observed in just about every type of condition you can imagine, including to the point where you walk outside and your shoes are absolutely soaked through from walking through the wet grass. So there is some benefits to the observatory there. And as for the second story, I suppose there's some benefits there too.
That's great. That actually answers 2 of our other questions. But Paul Markov wants to know, what do you use the first floor for?
I use the first floor for storing the boxes for my observing equipment. I keep my beekeeping equipment there, and on the off season, I'll move a few pieces off the that we want to store out of the winter. I'll move them in there too. But the idea was that I could build a warm room if I wanted to, and so far I haven't had the desire. I find that I'm quite happy sitting up there at the telescope, taking it all in and then packing it up. But like I said, I mean, I tried to future-proof a little bit too, and that's why I overbuilt and went a little bit bigger, because if I want to do some public astronomy with the local communities, I have that option with a 12-foot observatory, where had I built an 8-foot, it would have been perfectly fine for me, but it would have limited what I could potentially do with it.
Well, great, thank you. No more, that's it for questions, but we have one comment from Lewis who says, cool, Shane, excellent presentation.
Well, thank you.
And that's it. Thank you.
Thanks.
Absolutely. Excellent presentation, Shane. Thanks again. All right, let's move on to our next speaker, and that's Debra Ceravolo, and she'll talk to us about the colors of Emission nebula.
Should I go ahead?
Please.
Okay. Hi, everybody. My name is Debra Ceravolo, and I've been an RESC member for 27 years now. And excuse me, originally from Ottawa, and I've been in BC for almost 10 years. And I've been doing photography pretty much all my life, and astrophotography, I guess, since the Hale-Bopp days. And I got into deep sky imaging about 12 years ago. But I'd like to thank the Toronto Centre for inviting me to come and talk about my favorite subject, and that's colors in astrophotos, and especially nebulae. My presentation it's pre-recorded because the bandwidth here is not dependable, and I haven't subscribed to Starlink. So I guess this would be a good time to go ahead and run that presentation. Hi, everyone. Welcome to my world on Anarchist Mountain in British Columbia, Canada. We're at about 1,100 meters with a sky quality of around Bortle 3, which makes it really great for capturing faint objects like this soap bubble nebula. But it's not always clear, like this time of the year when the temperatures drop. It gets pretty cloudy. I'm going to show you in a minute. Yes, lots of cloud. Clouds above, clouds below, and a lot of the time we live in the clouds. So obviously not a lot of imaging going on then. But having a permanent observatory means that I have the luxury of being ready when it does clear. I'm having some fun with some time-lapse photography here. Here is a view of my observatory in much nicer weather in the summertime with the Milky Way. You might think that the scope looks kind of small in such a big 12-foot dome, and you would be right. There is a much bigger instrument destined to go in there. But this is a 12-inch astrograph, and I will show you the details of that in a moment. So this is what is intended to go in the observatory. It's been designed by my husband, Peter Ceravolo, and is actually going to fit in that 12-foot dome. It's a very fast system, about an f4.5. It's a 900 millimeter aperture, about 36 inches. He says it's 90% finished and 90% to go. He still has to finish the mirrors, but the mount shown here is running well and will be installed this coming spring. Just the mount. We will attach the existing scope on it until the mirrors are finished, but what a killer mount. No wind will move that around. I have been doing astrophotography for probably a dozen years now, and my approach and techniques in processing are always evolving. I tend to stay on an object for long periods of time, pretty much as long as it's visible overhead. I typically acquire 25 to 35 hours of data on any object now. This is a telescope I've been using for the past couple of years. The scope is a Ceravolo 300 millimeter astrograph designed by Peter, and it's a dual configuration, meaning I can swap out two sets of corrector lenses and go from an f9 or 2700 millimeter focal length to an f4.9 1400 focal length, sort of like a focal reducer for wider field, depending on the camera it's coupled to it. Here it's at f9 with an SBIG STX 16803 camera, and it has an off-axis guider and filter wheel set with Astrodon filters, sitting on a Paramount ME2 mount. With this setup, I can get about a 0.6 arc second per pixel resolution. And on the top is an Eagle 4 Pro computer that allows me to plug in all the cables for the cameras and the focuser and the mount and everything, eliminating the bulky power bricks and keeping everything neat and together. It's especially nice when the scope's loose, wires don't get pulled out or strangled. In this photo, I am swapping out the big 16803 camera for an Illuma 694 mono camera with its filter wheel. staying with the f9 configuration, giving me a resolution of 0.3 arc seconds per pixel, but a much smaller field of view. This is really a great setup for planetary nebulae. This camera doesn't have an off-axis guider, so I have attached my pointer here, another guiding camera with the mirror lens, and I can easily find a guide star better with this wide field. The problem with off-axis guider chips is that they're usually small fields and you may not be able to find a good bright star to guide on. I'll just quickly show how I do the acquisition and then move on to talking about color and nebulae. This is the Eagle Manager from the computer that was on top of the telescope you saw earlier. I log into it from inside the nice warm house remotely, and I can turn on the cameras and I make sure that everything is operational with all the USB ports. I look at the temperature and the sky quality meter. It's a really handy, nice little thing to have. So while I'm accessing the remote desktop, I can activate the SkyX software. That's the planetary software that comes with the Paramount. I can do many things with this software, but I mostly just use it to find my target and to slew the telescope. There's also a virtual hand paddle there where I can center the target if the pointing is not perfect. And I can also keep track of where the telescope is pointing all night and if it's getting too close to the horizon. For my main acquisition software, I like to use MaximDL. It connects the cameras, sets the coolers. It's also a scheduler where I can choose what filters will be used, how long the exposures will be, how many images to take, and where to download the images. MaximDL also controls the guide camera. For processing my images, I mostly use PixInsight where I can do all the calibration and post-processing, and sometimes I use Photoshop at the end. I prefer CCD monochrome cameras with separate filters because it gives me better control over color, and they are usually less noisy than one-shot color cameras or CMOS cameras. There are some CMOS mono cameras that are really good too, but I use what I have, and that's a couple of S-Big mono CCD cameras. Here I am taking apart a 7-slot filter wheel for cleaning that goes on an S-Big STX 16803 full format camera like the one you saw earlier on the telescope. These are large 50mm Astrodon filters. There's luminance, red, green, and blue, and 3 narrowband filters. Narrowband filters are a must for capturing the detail in nebulae as they isolate the emissions coming from the objects. So in order to talk about colors of nebulae, let's start with what nebulae are and how colors are created within them. I'm sure most of you probably are quite aware of what a nebula is, but I'll just talk briefly as I move into dealing with color palettes and my own technique that I've developed. We can colorize our images any way we want, and that's fine, but I usually like to better represent the object I am photographing more accurately. And in order to do that, I needed to tune into the physics to gain a better understanding of what's happening inside the nebulae. So here's a little science lesson. Throughout our galaxy, floating in space between the stars exist gigantic cosmic clouds of dust and gas. The extreme cold temperature causes the atoms in the gases to bind together and form molecules that coalesce into denser regions. Some of these dense regions of gas collapse under its own gravity and star formation begins. Very hot newborn stars energize the surrounding gas with ultraviolet light, making the clouds visible at optical wavelengths and giving us amazing things to see and photograph. There are basically 3 types of nebulae that are technically different from each other. There's the dark nebulae, reflection nebulae, and emission nebulae. Planetary nebulae and supernova remnants are also emission nebulae. Dark nebulae, like this Horsehead Nebula, are these irregular and familiar shapes made of dust clouds so dense that they obscure the visible light from behind, making them appear opaque. They are being backlit by bright ionized gases. The Pleiades on the right, M45, is a good example of a reflection nebula. This type of nebula typically shines with a beautiful blue color as the dust grains in the cloud reflect the blue starlight back to us. And this close-up of the Orion Nebula at the bottom is an emission nebula. This nebula itself is creating its own light. Note that planetary nebulae are still emission nebulae, but they have a different origin. Planetary nebulae are the expelled atmosphere of a single dying star that is in the process of collapsing. You can usually see the star in the center, like in the Helix Nebula here, and the center star in the Owl Nebula. The extreme hot core of the star has been exposed, and its intense heat is ionizing the surrounding shell. These are the hottest known stars in the universe and create fascinating and beautiful, colorful, and short-lived objects, usually roundish, like planet shape, hence its name. Most interestingly, this process will be the fate of our own sun. Many factors influence the color of emission nebulae, including the nature of the chemicals that make up the cloud and the degree to which these gases are being ionized. But I have also learned from experimenting with certain filters that the expanse of interstellar dust in and around the nebula and along our line of sight can alter the emitted color, and I will show what I mean about that later. Back to the Orion Nebula. This is a close-up of the core, and these hot young stars in the center here in the center is called the trapezium cluster, and they are radiating powerful ultraviolet light, causing the atoms of the surrounding gases to absorb all that energy. In simple terms, when the excited atoms settle down, they release that extra energy it absorbed as a photon that emits at a specific wavelength, and then we correlate that wavelength to a specific color in the visible spectrum. So different gases emit at different wavelengths. Again, I realize most of you know this stuff, but just a little review here. By definition, the visible spectrum is part of the electromagnetic radiation that human eyes can detect. This ranges from wavelengths of approximately 400 to approximately 700 nanometers. Hydrogen is by far the most abundant element in the universe, and naturally the dominant gas in emission nebulae. Other elements that also exist in the interstellar medium are helium, oxygen, sulfur, nitrogen, and there are others. So here are three of the most prominent elements in most nebulae: oxygen, hydrogen alpha, and sulfur, which became the most popular filters available for astronomical cameras. By the way, here's an interesting point. Color is a biological concept. Photoreceptor cells in the human eye, called rods and cones, respond to light waves, which our brain converts to our perception of light and color. We have three kinds of cones that are sensitive to different wavelengths. One kind is sensitive to short wavelengths, like the blue range. Another is sensitive to medium wavelengths, like the green range. And one is sensitive to long wavelengths, the red range. Color is not a feature of light, but only an impression produced by an electromagnetic wave of a certain length in the brain. In other words, color exists because our brain creates it. People's ability to see color vary, but for the most part, we all see similar colors, unless there is a deficiency, which can occur. I want to make a key point here. Any color is a mix of red, green, and blue in different proportions, giving us roughly 16 million colors that can be reproduced in an RGB image. So determining those three RGB contributions of a color, we can pinpoint and reproduce an accurate color of any wavelength. There is a way that we can do that in Photoshop, and I will show that in a moment. Cameras have filters that allow certain wavelengths through, and we can play with that in a multitude of ways. We can be playful with it or more scientifically accurate, whatever the astrophotographer wants to do. Right here, I would like to say there is no right or wrong way to produce an astronomical image, unless there's been an introduction of something that was never there, but that's a whole other thing. How someone colorizes their image is totally up to them. It's a personal thing. My thing tends towards the more accurate representation, but it is fun to explore and experiment. So here I will talk a little about color palettes. When talking about color palettes, you have to talk about the Hubble palette first. So a little history here. The Hubble Space Telescope captured this famous image of the Pillars of Creation in the Eagle Nebula way back in 1995. And the way they colorized it was for a reason. The scientific camera was not equipped with normal red, green, and blue filters, but instead hydrogen alpha, oxygen, and sulfur filters to better capture the structure and detail of the object by isolating the emissions. Now, in photography, there are three primary colors, red, green, and blue, that make up a naturally colored image. So to create a naturally looking photo with three narrowband filters, the Hubble imaging team had to force the narrowband data into the broad RGB channels. This is how the colors of Pillars of Creation came to be. Notice that H-alpha, sulfur emissions are both close together in the red end of the spectrum. The pillars was colorized by assigning S2 to the red channel, and instead of also assigning H-alpha to the red, as that would not differentiate the structure, it was colorized green. So they put H-alpha in the green. The O3 emission, the oxygen line, was assigned to the blue channel. But since hydrogen alpha was colorized green and is the most abundant gas, the Pillars of Creation was known to be predominantly green, and this combination became known as the Hubble palette. However, the Hubble palette is not the only way to combine color. Those three filters can be creatively rearranged in the RGB color channels to produce different palettes, with a wide variety of colorful and dynamic presentations. The palette names are acronyms, with each letter representing the emissions arranged in the order of the red, green, and blue designations. The Hubble palette, now known as SHO, is where sulfur, S2, is assigned the red channel, hydrogen alpha to the green channel, and oxygen to the blue channel. Another less often used palette, often seen in CFHT observatory images, is the HOS, where they put H-alpha in the red, oxygen in the green, and sulfur in the blue. Alternately, HSO has a pleasing result with more pinks and purple colors. The HOO palette portrays a more natural coloring with hydrogen alpha as red and oxygen as both green and blue, as O3 naturally resides between green and blue along the spectrum. The outcomes of these combinations vary depending on the object being imaged and the intensity of the different emissions from that object. Also, one can tweak each color channel to different degrees using contrast manipulation or curves and modifying the palettes. All of these palettes and modified palettes offer interesting ways to explore emission nebulae. Depending on the object and the palettes chosen, different structures in the nebulosity can be highlighted. Creating images from narrowband data using a variety of those palettes can make the star colors in an image look pretty ugly. This is M27 with the HOS palette. It is important to note that stars emit light over the entire continuous spectrum, and the narrowband filters don't allow that whole spectrum through. So they look smaller with weird colors, usually magenta. One solution to achieve properly colored stars in narrowband images is to acquire two sets of data, one taken with RGB filters for the stars and one set taken with narrowband filters for the nebulae. To summarize, you remove the unwanted stars from the narrowband image of nebulae and later replace them with the naturally colored RGB stars. There are image processing tools like my favorite Star Exterminator, a plugin for PixInsight, that can effectively remove the stars from the narrowband image while leaving the nebulosity intact. Also, further processing on the starless image allows the freedom to stretch out more detail without worrying about bloating the stars as they are later blended back in. Here I have removed the stars in PixInsight using Russell Croman's Star Exterminator, an amazing plugin that works really well, which looks kind of cool and would make an interesting photo on its own. By removing stars, we can often see much more detail in the nebula. The Star Exterminator plugin also creates an image of just the stars that it removed, which can be processed on its own as well, like using deconvolution, reduction, and then put back into the starless image. The result is an image with good structural detail in the nebulosity and properly colored stars. I won't demonstrate how to do all that because there are some really good videos on YouTube. I really think that good star color is important. So I take two sets of data when I'm imaging, RGB when it's dark with no moon, and narrowband data when the moon is out. Narrowband filters only let a sliver of light through, so that makes them great for moonlit nights and also in places where there is a lot of light pollution. So here is the before image, and here's after with the properly colored RGB stars. So can we have natural color using only narrowband filtered images? I think so. My approach is not scientifically accurate by any means. Keep in mind, there is really no such thing as perfect or true color, but we can get close. First, here I want to show a typical way to create a color image from monochrome images. This is a screenshot in PixInsight and how we put together master images to get a color image. Here I have 3 narrowband images. There's oxygen, hydrogen alpha, and sulfur. Or I could just have red, green, and blue, whatever. So you basically enter the names here in the channel combination into the red, green, and blue channels here. And you hit the apply button and a new image comes up in color. You can see there is sulfur in the red channel, hydrogen alpha in the green, and oxygen in the blue. That's the Hubble palette. I can switch them up and get different color palettes if I want. But here's the thing. By assigning the narrowband images to those 3 channels, we are telling it to be pure red, pure green, and pure blue. Remember, every color has a red, green, and blue component, and pure red, for example, has no green or blue component. Same with the other channels. So that's okay if you want your image to be one of those palettes I talked about. But if you want the color to be more accurate according to the narrowband's specific wavelength, you have to determine the contributions of red, green, and blue for each wavelength. I have found the best way to determine the red, green, and blue values for each wavelength is to use the color picker tool in Photoshop. There I open a calibrated spectrum with the wavelengths in nanometers created by Andrew T. Young of San Diego University here. I can get a close approximation of the combination of red, green, and blue components of each wavelength by touching on the number of the wavelength in nanometers on the spectrum for each emission with the eyedropper, and here is showing it's touching around 656 nanometers, which is the wavelength of hydrogen alpha. Then we are given the information we need in the color picker tool. So here we have the contribution of the red, green, and blue values that make hydrogen alpha, and you can see that there's no green contribution, but there is a blue contribution. In the past, I have stayed in Photoshop and used hue saturation layers to enter the values and colorize the image because I didn't know how to do that in PixInsight. But now I have been collaborating with a friend, Tim Hutchison, who figured out a way to do the same thing using a process in PixInsight called pixel math. That allows me to state the red, green, and blue contributions of each wavelength and then tell it to combine the images that way. I won't bore you with the nerdy details of the math, but Tim converted the information of each emission to the PixInsight standard of measuring color and the coding which makes the pixel math work. So that is the basic idea of colorizing nebulae, and I will show you some finished examples in a moment. But right now, I want to take it a little further with some imaging work that I've been doing for the past couple of years, and that is working with a rarely used filter, hydrogen beta. This is probably better suited for a whole other talk, but my work with hydrogen beta has been interesting and I think can show us a different way of appreciating the dynamics of nebulae. Some may think, what's the point? It's still hydrogen. The structure should be the same, which it mostly is, but there is something else interesting about it. It emits in the blue end of the spectrum. Hydrogen possesses many other emission lines that exist throughout the entire electromagnetic spectrum, even beyond the visible. You can see 4 of them here in the visible. But the second brightest hydrogen line after hydrogen alpha is hydrogen beta. Here at 486 nanometers, the blue end of the spectrum, making it an interesting contribution to an image. If hydrogen exists anywhere in space, hydrogen beta is there too, along with all the other lines, albeit fainter than hydrogen alpha. However, galactic dust will be the defining factor of how much we can see it. Dust can attenuate hydrogen beta, much like the reddening of the sky at sunset, where blue light gets scattered by the atmospheric molecules near the horizon. And so likewise, galactic dust can scatter the fainter blue hydrogen beta light, leaving the red hydrogen alpha to dominate. Like here on the left, the Gecko Nebula is very red naturally. I'm assuming there is a lot of galactic dust there. Not so much H beta is getting through. It's there, but it's getting scattered. Remember, wherever there is hydrogen alpha, there are all the other hydrogen lines too. But where there is less galactic dust in the region to scatter the blue emissions, hydrogen beta shines through, causing the nebula to appear more magenta, as you can see here in the Orion Nebula. The resulting colors I get with the combination of using hydrogen alpha, hydrogen beta, and oxygen filters and mapping them according to their spectral wavelengths is different. This is a basic diagram of mixing light and is known as the additive color theory. When all the primary colors are added together, the light is white. When there is no color or absence of color, there is black. Our sun is white light that holds all of the colors we see. This only shows the primary and secondary colors, but of course, there are many more combinations. And it's very simple, but depending on the intensities of the intermingling of different wavelengths, you get a variety of color, and the more colors involved, the lighter the result. On the right-hand side, you can see the bubble nebula, and on the edge of the bubble nebula is kind of a gold color, which is a combination of the oxygen and the hydrogens. And you can see the pink nebulosity all around it, which is showing the H beta shining through in the background there. So without galactic reddening of the hydrogen gases, you will see the magenta. Here's an interesting fact. Back in the film days, objects like the California Nebula and Horsehead Nebula looked really red because film was not that sensitive in the blue end. It wasn't showing the hydrogen beta contribution. The film in those days was actually optimized and intended for portrait photography, so more towards the red. So the green-blue oxygen also interacts with all the other emissions, creating varying shades of pale greens and yellows, like in the bubble. By understanding how light color theory works, we can begin to appreciate the dynamics of the dust and gases in space. Finally, here are a few images that I have processed using hydrogen alpha, hydrogen beta, and the oxygen filter, and color mapping them using the pixel math method. The photos have had the narrowband stars removed and the RGB stars inserted at the end. You have already seen the bubble nebula and the trapezium in the Orion Nebula. This is the elephant trunk nebula in the constellation Cepheus. I think it looks more like a dragon's head. The intense emissions around the snout here, see the dragon head here? There's like his nostril there. The intense emissions around his snout here are very magenta, so you would think less dust there. It makes me wonder if the intensity of the ultraviolet radiation from the new stars is pushing away that galactic dust. This is NGC 7000, or the Cygnus Wall. That's part of the North American Nebula. And there's lots, you can see there's lots of hydrogen beta, very strong in this image. The Running Man Nebula, which is just above the famous Orion Nebula. Actually, Orion Nebula is off in this direction over here. And it's very pink and lots of H beta shining through there. And of course, it was spectrally mapped like I showed earlier. And of course, the famous Horsehead Nebula. It's kind of red, but also a little magenta. So a lot of galactic dust there, but the hydrogen beta is still contributing to the overall color. This is a Crescent Nebula, and it's pretty wild. The teal O3 is strong, and those light yellows is a combination of hydrogen and oxygen, the red H alpha in the crescent and hydrogen beta in the background. This looks like a supernova remnant, but it isn't. It's an emission nebula. It was formed by the fast stellar winds of a massive, really energetic dying Wolf-Rayet star colliding with and energizing the slower moving winds it ejected at an earlier time. That resulted in a shell and two shock waves, one moving outward and one moving inward. So much structure there. Lastly, this is the Soap Bubble Nebula. Notice the light yellow in the outer rim of the shell where oxygen and hydrogen are overlapping. The background has lots of rich magenta due to the less dust there. This is a very faint object, and I got 45 hours of data on it. By the way, this kind of imaging is very intensive and requires Zen-like patience and really good guiding, and basically I threw out about 25 hours of data. So doing this kind of imaging is really hard and takes a lot of patience, which I don't always have a lot of. But we astro imagers are all really crazy anyway. My cat will attest to that. He is telling me, enough of this image processing and feed me. How we choose to display our celestial photography is an individual choice, but there should also be a consideration of the object that we are capturing and disclosure about how we are representing it. Color is an important and powerful tool, and the colors of the universe can teach us a lot. Thank you for listening. Okay. Any questions?
Uh,
I can't hear you, Paul.
I have to repeat what I just said? Okay. All right. So I'm told that I have to repeat what I said. I said, Debra, fabulous presentation and, of course, great images. And thank you very much. And I'm glad that I found you on the internet and invited you over to speak to us. Let's go to questions.
Great. We got a few questions in here. First question, at what elevation is your observatory?
Oh, the elevation is about 1,100 meters, which is about 3,600 feet. We're actually about 2,000 feet above the valley floor in the Soyuz.
Great. Okay, next question. Considering that HO has a more natural feel as opposed to, say, HOS, at least to my eyes, do you consider this an indication of S2 basically providing additional information with regards to the hydrogen alpha filter?
Sorry, I don't get the question.
Okay.
Just repeat that. I can't read it.
Yes. So considering that HO has a more natural feel as opposed to, say, HOS, at least to my eyes, do you consider this an indication of S2 barely providing additional information with regards to hydrogen alpha filter?
It's just more natural because oxygen resides both in the blue and the green and is really a teal color than anything else. So the HOO palette is basically correct in the mapping. But the sulfur is an interesting filter on its own. It actually allows through a very different structure than H alpha. So that's why the Hubble palette comes through so well, because it really shows the difference between the sulfur and the oxygen. So the sulfur, yes, sure, they're both kind of close red in the spectrum, but they both offer different structures of the subject itself. Does that make sense?
Yep. Okay. Next, we have a comment from Peter West who says, "Thank you for including a basic explanation and not assuming some of us actually know anything. Simply amazing presentation."
Great, thanks. I wasn't sure, where to go from the novice to the more advanced, but I just kind of like put it somewhere in the middle there.
Next, we have a comment from Guy who says, should we just skip S2 for using hydrogen alpha for nebulas? What should be green if it was not oxygen 3?
Well, it all depends on what palette you want to use. I wouldn't skip the S2. I actually, because I use the H beta all the time now, I took my S2 filter out because I only have 7 slots in my filter wheel. I use luminance, red, green, and blue, hydrogen alpha, hydrogen beta, and oxygen. But sulfur is actually, sometimes I wish I had it because some objects show a very strong structure detail in sulfur, depending on the object. Like for example, the Helix Nebula has very strong sulfur structure that whatever channel you put it in, even if you combine it with H alpha, it will show through and add to the image.
Great, thank you. Next up, we have, Guy also says, why did I purchase that S2 filter for crying out loud? To which we did actually get a response in the comments from Eric Briggs, who said that CCD imagers are very sensitive in the red, so S2 is trying to be your friend. What do you think?
Yeah, I mean, S2 is a good filter. I would like to get back. Maybe I'll get a new filter wheel that has 8 slots, and I'll put my filter, the S2 filter in there. But it's not a waste of money, that's for sure. But it can be color mapped like I did, and just included into the image the way I do my image, my mapping, just the same way.
Follow up to that, we actually says, just wondering how much extra information I can get from S2 when I already have captured an hydrogen alpha imaging run.
Well, like I said before, S2 can offer a very different structure.
Right, of
than
course.
the H alpha.
Next question comes in from Lewis, who asks, how many different cameras do you use? Do you have to update them often?
Updating? No, I have mostly S-Big cameras that I've had for a long time. One's the 16803, the really large format, and the other is it's a 694, which is a 4-micron camera that I love to use for with my F9 setup, which is like really high resolution for galaxies and planetary nebulae. So I basically just mostly bounce between the 2 of those cameras, but not often because it's a lot of work to change out.
That makes sense, yeah. We got a question in from Warren Gallagher, who wants to know, does the star eliminator have a problem with larger star-like objects?
You mean the Star Exterminator?
Yeah, I think so.
The software. I find that what was it called? StarNet Plus in the past in PixInsight was terrible, and it really had a hard time with large stars. But the Star Exterminator, I'm actually really impressed with. It does an excellent job on the small stars and the large stars in particular. So it's very much worth the small cost, I think. It's actually Russell Croman's processes that he's created. Another one called Blur Exterminator are real game changers in the image processing world right now.
That's very cool. Question coming in from Aiden B, who wants to know, how much of the hydrogen delta and gamma wavelengths are you able to get in your photos?
Well, I don't get the delta and gamma at all because I don't have the filters, for one thing. And they are very faint, but it's not to say that I won't do that one day. I will. I think normally when I do an image, I go very deep, probably somewhere between 25 and 35 hours for every object. And I tried to get as much or equal data with everything. Like if I get, say, 20 hours of H alpha, I'll try to go for 20 hours of hydrogen beta as well, and then the gamma and delta. But it's not an easy thing to find those filters right now, unless somebody comes up with making them mass produced.
That's great. I think that's the last question for tonight. Thank you so much.
Great. You're very welcome.
Deborah, one comment from myself. I was watching the presentations on two different monitors this evening, and while looking at your images on the two different monitors, the color rendition was quite different, which highlights the importance of monitor calibration. Do you do that, and how is it done? Deborah, can you hear me? Hello, hello. Deborah cannot hear me. Can anyone hear me? Okay, but Deborah couldn't hear me. No. Okay, I suppose we'll have to skip my question and we'll carry on with the program.
I
Tom
can't hear
Luton, our
Paul.
president, will take care of the announcements next. Go ahead, Tom.
All right. Well, thank you very much, and thank you very much to all our presenters this evening. It's been a wonderful, wonderful evening. So yeah, let's get started with our announcements. So this is one of two types of meetings we have here online. And yes, we were intending originally that this would be our return to the Ontario Science Centre. But what happened is that the bug that is currently going around is bad enough that it knocked important members of the AV committee for a loop, to the point that a whole bunch of very important preliminary work just could not get done. And as a result, we're not in a position yet to be able to present live in person. We are still planning next month at this point. Fingers crossed. I want to be back at the Science Center as much as you do. Two types of meetings. Recreational Astronomy Night, we've just finished up, and we're going to be having one of our speaker nights in 2 weeks. If you're joining us live on YouTube, please use the YouTube chat, say hello. If you've got any questions for the presenters, like other people have done so, please enter them in the chat box. If you're a new member, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're from. I am speaking to you from my couch here in Toronto. So the details of our next speakers night are still waiting to be finalized. It will be on Wednesday the 18th at 7:30 p.m. here live on YouTube. Our next Recreational Astronomy Night is the 1st of February at 7:30 p.m. Francois Van Heerden will be discussing the sky this month. And as Paul said earlier, we've got 2 open slots for presentations. If you've got something you'd like to present, please drop Paul Markov a line. Coming up with the DDO in the next little while, this Friday at 7 p.m. Speakers Night, Dr. Sarah Regeimer on how to find life on another planet. Registration links are available at rasto.ca. DDO Planetarium Day on Sunday, January the 8th, 2:30 p.m. Again, registration links are on rasto.ca. On Saturday, January 28th, at 7 p.m. is DDO Up in the Sky. And Sunday Sun Gazing on Sunday, January 29th, 12:30 p.m. to 1 p.m. And again, registration is online and the links are found at rasto.ca. The weather is the weather at the moment. There's been snow, there's been rain. I don't even know what the condition of the road is to the observatory at the moment. But we are taking bookings, and access to the CAO facilities is by members and families only in a modified communal fashion with a total site occupancy limited to 25 individuals. The upstairs booking is for upstairs, or the upstairs washroom is for upstairs bookings only. For max occupancy for upstairs bedrooms of 2 people from the same family per bedroom, total of 6. Communal areas limited to 3 people wearing masks. All CAO users can use both kitchens, downstairs washroom while wearing masks. The full details are on the website. Please read everything before you make any bookings. We are currently looking to fill a few roles on our volunteer job board. We're looking for a website manager. We're still trying to find an education and public outreach chair, looking for a light pollution committee chair and a volunteer committee chair. We'd like to get a marketing committee formed, so we need a chair and members for that. The AV committee is always looking for additional help. Education and public outreach is also looking for additional help, especially online presenters and telescope camera operators for virtual star parties. A reminder that to volunteer, you first must be a member of the Toronto Centre. Please contact myself at president@rascto.ca for more info. Just a reminder about RASC membership. You can renew or sign up online at secure.rasc.ca, and gift memberships are available. Contact the national office at mempub@rasc.ca for more details. And with that, I'd like to wish you all a very good night. Thank you very much for joining us. Please follow us on all of the various forms of social media that we've got listed here. If you've liked what you've seen tonight on YouTube, please like and subscribe and click the notification bell. Be safe, keep looking up. Good night, everybody.